This is installment 5 of a series of lectures on special relativity. This is an especially interesting lecture. It's basically the culmination of everything we've been talking about before, but from a completely different point of view. What we're going to do is I'm going to show you how momentum and energy in special relativity can be derived using variational methods that one uses in classical mechanics, for instance. So there's going to be a variational formulation. What does that mean? Well, first find out what the outline of the talk is going to be. I'm going to give you first a review of something called the action and the origin of something called the Euler-Lagrange equations. Now, familiarity of this prior to this lecture would be of great advantage, but you can probably follow what's going on anyhow. There's a whole field of variational mechanics called Lagrangian mechanics. There's Hamiltonian mechanics, and the mechanics basically is just saying that, well, what's the mathematical mechanics that you do to derive equations of motion via Lagrange method or via Hamiltonian methods? And they're both based on taking something called the action and minimizing it, basically. Given this background, I'm going to show you that if you assume a particular Lagrangian in classical mechanics, and you just go through the procedures that are already well studied and well defined optimization techniques, what you get is you get the energy momentum relationship from before. So let's see this. The last thing is going to be using very minimal information about the action, namely that the proper rate of change of action is invariant or constant, and you just assume that one thing in Hamiltonian mechanics and everything else follows from that. Well, let's start with the review of the action. What is action? Action S it's a functional. It takes Q here, which is a vector. Q is a trajectory. Imagine Q can be any trajectory in an n-dimensional space for a system of particles, whatever. Whatever Q is, however Q is evolving in time, if I have something called a Lagrangian, and it's a function of Q of t and its velocity Q dot of t, and perhaps t itself. And I just simply integrate that function, and I compute the value of it for a given Q. I get a value of S. So different paths give me different values for the action. Typically, in the vast majority of classical mechanics, the Lagrangian is simply this expression here. It's the kinetic energy minus the potential energy. And if one does this, all of Newtonian mechanics becomes really simple. It greatly simplifies the whole thing. Basically, there's no requirement to know anything about forces and balancing forces or anything like that. It all follows from energy arguments and optimization methods. So what are the units, just out of curiosity? The units of S are energy times time. So one view of S is that it is the average difference between kinetic and potential energies. Another interesting set of units here is that there's this R cross P. So this is position cross momentum. That's known as angular momentum of a particle, for example. So on the one hand, S action has units of energy times time. On the other hand, it has units of angular momentum. We won't dwell on that. We're going to stick with this first one. It's energy times time. Sometimes you may be interested to know how the action evolves in time. In other words, this is over a fixed time interval here. And perhaps I start at some initial time and I want to view what's happening with the action as time evolves. When you do that with these upper and upper limits of integration, it's sometimes referred to as Hamilton's principal function. Now, there's this one very, very huge axiom in mechanics and pretty much all of physics. There is this thing called the principle of least action. The principle of least action says that whatever, if I take this, in particular, if I take the Lagrangian as the kinetic minus potential, if as long as I know that, then the system will evolve so as to extremize, which could mean minimize or maximize, either or, doesn't matter. So it could evolve to extremize the action over all possible paths. So what nature does is it tries to optimize this integral S, called the action. And if you've seen derivations of this before, just this principle this principle leads to the following question. If I'm trying to take the action and I want to find a trajectory Q that minimizes S, what is that Q that minimizes that S? And it turns out that Q has to satisfy a set of differential equations, which are referred to as the Euler-Lagrange equations. So this is this. We're not going to derive that here. I can perhaps do this in a different sequence of lectures, but this Euler-Lagrange equation says that if I take the partial of L in the dot coordinates or velocity components, and that derivative has got to equal the partial of the Lagrangian in the position coordinates. And it leads to a natural definition of momenta pi as being the partial of L in the velocity components. So this is derivative of momentum in t, basically force components, is equal to time derivative of this partial, and that's equal to this thing. And this is a necessary condition for the minimizer of the action. So what's next? Well, what does this look like in reality? It's quite an abstract concept. I'm putting up one example here. For small angles, and if you have a pendulum that's swinging with a mass m under gravity g, and you look at a small angle formula for the Lagrangian, you can compute it. And let's not worry about how we got that, but this is basically kinetic energy minus potential energy. And if you look at those equations, if you look at the Euler-Lagrange equations for this, you'll have derivatives in theta dots and derivatives in thetas, and you write everything out, and you solve it, and you say, look, initially the angle is initially pi over 4, and the initial velocity, angular velocity, is 0. And you figure out, well, what does the Euler-Lagrange say? It says that the action turns out to be this very specific trajectory. It's pi over 4 times cos t. And that's what nature does. So if you wanted to compare the action at this extrema, so this is the answer. This is what nature does. It is the extrema. It's the thing that's minimizing S. So that's this thing in red. Let's suppose I want to see, well, what would happen to the action near the extrema? So what I'm going to do is I'm going to add a little variation of the trajectory. So I'm going to take this trajectory and I'm going to add a smallish variation to that trajectory. So I would expect that this action in blue with the variation should be bigger in some sense than the best or minimal action in theta bar. These things you can plot as a function of time. So the red thing is what nature does. It picks out this theta bar, which is this oscillation of the pendulum. The angle is changing in time at a certain frequency. But if I added this say second Fourier component to that and examine what the action did, well, it does something radically different. It oscillates in peculiar ways, but it just keeps on growing and growing and growing. So the principle of least action, when you look at the extrema, they're not fixed points. The extrema are functions, and the variations away from them give you actions that grow typically. This is the most modern approach that you'll see regarding special relativity. It basically starts with an assumption. You'll see this in some texts. They'll say the Lagrangian of a free particle is, and they'll state it. And here it is. It's m naught c squared with a minus sign, and it's got something that looks like this gamma factor, but it's plus 1/2, not minus 1/2 power here. And the v squared is the sum of the x dot squareds. So that's the velocity as observed in frame K. So I've got this Lagrangian, and the assumption is that in special relativity, the dynamics are determined using this Lagrangian and the principle of least action, specifically in the Hamiltonian mechanic formulation. Before I begin, this Lagrangian is strikingly not equal to the kinetic energy. So this is a little weird, but we'll just leave it at that. So what do? If you take this Lagrangian to be the correct relativistic Lagrangian for a free particle, then I can compute the momenta. And the momenta is the partial of that Lagrangian in the components of the velocity. And if I do that calculation, I'm going to take the derivative of this thing in the VIs. Every time I take the derivative, the chain rule, it'll lower this to a minus 1/2, and it'll give me a factor, gamma, a square root of 1 minus v squared in the bottom, which is this thing I'm highlighting in blue right there. So I do the partial derivative of this in the xi dots, and I get what I got before on the previous lecture. I get that the momenta is this m naught times the gamma factor times the 3 velocities. And this is true for each one of the components. So I can write this whole thing as a 3 momentum vector. And that is exactly the same momentum that we arrived at before by other means. So one thing to notice, this, if you have the Lagrangian, this is an easy calculation. You get it. It follows. It derives from. So if L is this, then the momenta must be this. And it's that simple and that quick. Well, the Euler-Lagrange equations also tell us something else. So if I'm minimizing the action for this Lagrangian and I write out the Euler-Lagrange equations, that says that this momenta we just derived, its components change in time according to the Euler-Lagrange equations in blue. But there is no xi in this Lagrangian, so this right-hand side is 0. What does this say? It says the time derivative of pi in t is 0 for each of the 3 components. Therefore, the momentum is constant, i.e. the derivative of the momentum vector must also be 0. So right on one page we get, if the Lagrangian for the system is this, then I know I have a formula for the momentum, and I know that momentum is conserved. How do we get the energy relation? Well, this you have to know a little bit about Hamiltonian mechanics, but just accept this first thing and the rest will follow nicely. The Hamiltonian of a physical system is a function of the position and the momenta. And it's defined, that's what this triple equal sign here means to be the sum of the momenta times the velocities over all three components minus the Lagrangian. Why? Well, if you do that, then H turns out to be the energy of the system. If L is T minus V, then this whole thing becomes T plus V. And the algebra also becomes easier. So H is just, to think of it as basically, it's primarily the energy of the system, whatever it is. Well, we already computed what the momenta were. That's this expression here. And it's got this factor of gamma sitting in here. So I'm color coding this. So that gamma, if I write it in explicitly, is this red expression here down the bottom. And then I've got an m naught vk on the top. So the k component of the momenta is equal to m naught vk divided by this square root of this red thing. The reason I wrote this out is that I wanted you to see that if I'm talking about k equals 2 on the top, I got a v2 on top. There's also a v2 embedded in this denominator. All right, so this defines a coordinate transformation. These are actually three equations for three unknowns, depending on how you look at it. If I know what v is, I can compute what p is. So in other words, if I know what v1, v2, v3 is, I can find p1, p2, p3. Those three equations can be inverted so that if I know what all three of the pk's are, then I can find out what the vk's are. That's what this thing up here is saying. It's saying that, look, this is the Legendre transformation tells you how to convert velocities into momenta. And that's basically this set of equations. So we have to solve that. How do we solve it? Well, okay, the system of equations. First thing I'm going to do is I'm going to say, if I square each of these components and sum them, I get the magnitude of the three momentum squared. That's this. And that means just square this and sum. So I get the same denominator squared on the bottom, and I get a sum of the m naught squareds, vk squareds on the top. Well, that turns out to be this expression here. Now, if you look at that, this thing is p squared equals something with v's. And all I want to do is I want to solve for v now. I want to solve p squared equals this for v. So if I do that, I can write out this expression as p is equal to this, but when I invert to find v as a function of p, I get this expression down here. It's this one right here. Looks a little bit different. And then once I have v, that means I can put this expression here, this v, back up where this red term is. And that means I can replace all of that with things that only have p's and m's. And that goes in the bottom. And therefore I can solve for vk's in terms of the pk's. And what you get is this red expression. So in summary, with the momenta being defined using the partial of L in Q dot, that gives us a way of translating Q dot or velocities into momenta, and vice versa. And I've just figured out the inverse of that. So that says that now if I know the momenta, I can compute what the velocities are. So I'm going to use this last blue expression in the Hamiltonian definition. In particular, this last blue expression here has got a formula for the VKs. The VKs sit in this Hamiltonian right where I'm highlighting right now. So I can take these VKs and put them in there. I can take these VKs and put them in there as well. And then I'll get something on the right-hand side which only depends on position and momenta. So let's see that done. And I got a theorem out of this. So I start with the Hamiltonian. I'm going to replace those xk dots with the formula that I just derived in the previous slide. And that's this red formula here. And I got a sum of these expressions here. And if you look at them, I got a pk times a pk. So I'm going to be summing the squares of pk's. And when I do that, the sum of the pk squareds are just p squared. So this whole thing here on the first term will give me this top expression, just this top term, this p squared c term here. And this L is the L that I was given in terms of the velocity, re-expressed in terms of the p. So Hamiltonian is this sum plus that Lagrangian, and it simplifies a little bit down to this. I've got a common denominator, and I look at the top, and I say if I factor out c, the top is the same as what's underneath the square root, and I can simplify it, and I get that the Hamiltonian for the free particle is equal to the energy is equal to this expression here. If you square both sides, you get something called the energy momentum dispersion relation that Einstein famously first derived. This was in fact how Einstein he got this expression, the energy dispersion relationship. And once he had this, he said, look, if the particle has no momentum, then it's at rest, and I get E equals mc squared. He also said, well, if the particle has no mass, such as a photon, then I can get an energy momentum relationship for the photon. So he did both, really. It's not just E equals mc squared. It's also the momentum of the photon comes out of the same energy dispersion relationship. Okay. Last thing is, everything I said there, that it follows out really pretty, very nicely. If I have the Lagrangian and I assume Hamiltonian mechanics, then for that Lagrangian at the very beginning, which was an assumption, everything follows out perfectly. A question might arise is, well, how do you get that Lagrangian in the first place? I mean, why that Lagrangian? It's not even the kinetic energy. So I'm going to present one way out of that. And this is a little atypical. It's not normally described in this manner. What I'm going to do is I'm going to write down an axiom that simply says, in blue, the proper rate of change of the action of a free particle is a Lorentz invariant. That means that the proper rate of change of the action is some constant, so that it's constant in k and k prime. Well, what is the proper rate of change? The proper rate of change is the rate of change with respect to the proper time. So this axiom written out in math says basically that there should be some constant E naught. I don't know what it is, but I know it's got units of energy. That whatever it is, the rate of change of action with time, with proper time, is equal to minus E naught. Well, this is the simplest differential equation possible. If this is true, then I can integrate both sides in tau to get S. So S must be minus the integral from a tau 1 to a variable tau of E, the constant E naught d tau. Well, if you go back to the definition of proper time, I can do a substitution and I can replace tau's with t's. And when I do that substitution in the integral, you get this expression here. In other words, if the proper rate of change is this constant, then the action must be given by a formula for the Lagrangian, which is almost identical. It's just slightly different. It has the Lagrangian has got to equal minus some constant that I don't know times the square root of that. Well, that being the case and not knowing what E naught is, I can simply go ahead and do everything else I've done before. I can define momentum of this as I take the partial of these things, of the Lagrangian in the velocity components, and you get a formula for that. When you do, turns out it implies something almost identical, that the momenta is some function of v times the velocity, 3 velocity, and that function of v has got to be E naught over c squared times this gamma factor. At this point, you might want to say that this m of v is a relativistic mass. You could think of it that way, but mathematically, it's just some function. We don't know what it is. It's some function of v. Who knows? We can call it whatever we want. But what we do know is that when the particle is not in motion, when v equals 0, that whatever this function is, we'll give it a value. M of naught is equal. M at v equals 0 is going to be defined to be this m naught mass. So a reasonable thing to call that is the rest mass. So if that's the case, and I look at this formula, then it must be that the E naught constant must be the rest mass times c squared. And when you have that, then the Lagrangian is the same constant that we had before in the previous discussion, and the same factor here. So how do I get the energy dispersion relation? Well, now I'm back to square one. I'm back at the very same Lagrangian that we had before, and you go through all that procedure and you derive what the Hamiltonian is, and then you get an energy dispersion relation exactly the same as before. So this is interesting. It says if the action of the particle is decreasing at a constant rate, E naught, which is its rest energy, then it must be the case that this energy dispersion relation is true, and that E equals mc squared when momentum is 0. So what does that possibly mean? Well, I'm going to go off script here, and I'm just going to give a sort of a pseudo physical argument as to why this might be true. One physical interpretation is that the particle, for a particle to move through space-time, action must be expended to do so. That means ds d tau has got to be negative something. And it could be that this is a property of space-time itself. Possibly of space-time, possibly a property of the particle, perhaps both. But when you look at it that way, what it looks like the particle property of rest energy acts like a thrust rate, because the rate of change of action is constant. It's equal to this constant thrust of minus E naught. So I view it as like a particle going through molasses, and there has to be a constant force pushing it through the molasses, and the force is given by E naught. But that's all just metaphysical mumbo jumbo. What really matters in all of everything that I've done up to this point, there's two things. One, the Lorentz transformation, and two, how do you figure out what momenta and energy and velocity is in special relativity. That's pretty much all the other lectures. But at the very end, I've stopped here in my development of special relativity with this energy dispersion relation. And this is a really big deal. This energy dispersion relation, this is more than just E equals mc squared. And the reason for that, I believe, is that it is absolutely paramount to the development of relativistic quantum mechanics. Now, as at this time in history, we know that there's no connection between general relativity and quantum mechanics. But there is a special relativity version of quantum mechanics. It's the closest that we've got to combining those two branches of physics. And in 1927, Dirac, he initially started with this dispersion relationship. He said, well, E is plus or minus the square root of this thing that's got momentum terms in it, and these m squareds and c to the fourth terms in there. And he said, you know, if I was trying to make a quantum theory out of this, the really, really short version of how that's done is that energy and momentum are actually operators in a Hilbert space, and they're given by these expressions down here. And this was already known by Schrodinger in the sense that if you make those assumptions, you can solve the hydrogen atom perfectly, and it works wonderful. But Dirac looked at this expression and he said, "Look, I can't put these operators, these differential operators, underneath a square root sign. What does it mean? What does it possibly mean to have the square root of a derivative? So he looked at this long and hard. He said, wouldn't it be wonderful if this thing was in fact a linear operator? In other words, suppose that I could somehow complete the square underneath here and get a sum of linear, something that's linear in momenta in particular. And when you try to do that, and you think of these as just being numbers, you can't do that. It's not possible. However, what he realized was that if all of these things became matrices and matrix operators, then that was possible. And after a long discussion, after he solved that, he derived an equation here in blue saying that if this is the energy dispersion relation, then and these are the operators that define energy and momenta in quantum mechanics, then I don't get Schrodinger's equation. I get Dirac's equation for the wave function. And the wave functions are actually spinors. They're four-dimensional wave functions. And in there's this alpha thing here. That's actually a 4x4 matrix. And this beta is also a 4x4 matrix. And this equation works even better than Schrodinger's equation. And what Schrodinger did was basically said, if I don't have a relativistic theory of quantum mechanics, I do have the regular energy dispersion relation for a free particle. It's just p squared over 2m. E is equal to p squared over 2m is the total kinetic energy. So if you use that and you use these differential operators, you get Schrodinger's equation for the free particle. So Schrodinger did this first, and then Dirac did this second, and all they're doing is taking an energy dispersion representation of the energy and momentum operators, and then deriving the wave the function for the wave function, the formula for the wave function. So this thing in blue that Dirac got, it's the basis of pretty much all of modern physics. And when in certain conditions, when the velocities of the electrons in the hydrogen atom are very high, there are relativistic corrections to what Schrodinger predicted. And they are explained very well with Dirac's version, more general version, using Einstein's energy dispersion relation. And another thing that popped out of that was that this plus and minus Dirac could not rectify initially. He said there's a plus and minus sign that can't, what is that all about? And what he did was he figured that there must be other kinds of particles, antiparticles. And the plus and minus basically gives you two particles of opposite energies that when they collide, there's no energy. That gave rise to the whole notion of an antiparticle. That's why this development was especially topical for today even. How do you get the correct energy dispersion relation before you write down the quantum mechanic formulas? And with that, we will finish.